last class we have seen axial deformation of a bar, we have seen how to derive the differential equation and how to use variational approach or Galerkin approach to get the element equation system. And once we get element equation system, what we did is we solved a problem, a stepped bar problem subjected to axial loading, and there we have seen how to assemble how to discretize the given problem and also how to derive the element equations, and then how to assemble the element equations to get the global equations system, and how to apply the essential boundary conditions which are displacement boundary conditions. And then after solving the global equation system, again we go back to each of the element and get the solution of the stress, strain and axial force in each element. So we have seen that for a stepped bar problem, and also we have seen what is the physical interpretation of stiffness matrix. Ith column of a stiffness matrix is nothing but it gives us an idea about the force required to have unit displacement at ith degree of freedom with all other degrees of freedom values equal to 0. And also we have seen how to get the spring element, the element equations, and also using the element equations that we derived for a spring and also axial a bar under axial deformation. We also solved a coupled problem or a problem in which you have spring and also a bar, a spring bar assembly problem we have seen in the last lecture. And today's lecture we are going to look at how to analyze truss members, analysis of 2D and 3D trusses we will be looking in this lecture. And before we look at the derivation details, let us see what are truss members. Trusses are structural frameworks in which individual members are designed to resist axial forces only. They are commonly found in roof structures and bridges. The equations for these elements are well known in structural engineering field and usually are covered in traditional courses on matrix structural analysis. Element equations can be derived from axial deformation element using simple coordinate transformation. And if you look at the figure that is shown here, a 2-dimensional truss element is shown there, and a 2-dimensional truss element is an axial deformation element oriented arbitrarily in 2-dimensional space. And in the figure you can see a local x coordinate system along member centroidal axis from node 1 to 2, and global coordinate system in Cartesian coordinate system defined as or identified as capital X capital Y, and the local coordinate system is denoted using small letter x. All the truss elements in the model are referred to this global coordinate system, that is capital X capital Y. The nodal displacements in the local coordinate system are denoted using small d1 small d2, and the corresponding applied forces are denoted using capital P1 and capital P2. These are in the local coordinate system, and these displacements and forces they get resolved in the global coordinate system, or the global degrees of freedom are denoted using small u1 small v1 at node 1 and small u2 small v2 at node 2. Similarly, the force at node 1 in the global coordinate system is denoted using capital F 1 x, 1 x is subscript capital 1 f y in the y direction, in the global y direction. Similarly, at node 2 capital F 2 x capital F 2 y. So, at node 2. So, these are the forces and displacements. So, now since the element is based on axial deformation equations that are derived earlier, the same sign convention will be following here, that is if a tensile force is assumed to be positive and a compressive force is assumed to be negative. And in the local coordinate system, the displacement vector is d1 d2, and in the global coordinate system displacement vector will have 4 components u1 v1 u2 v2. Similarly, the force in the local coordinate system is consists of 2 components capital P1 capital P2. In the global coordinate system the force vector consists of 4 components f1x, f1y, f2x, f2y. And now let us see the element equations for axial deformation element, which we already learnt in the last lecture. E a over L 1 minus 1 minus 1 1, and d1 d2 is the local displacement vector, capital P1 capital P2 is local force vector, and this can be compactly written as k subscript L. L stands for local coordinate system, and d subscript L is equal to r subscript L. And here in this element equations, capital E is Young's modulus, capital A is area of cross section of element, L is length of element. And now let us see what is the transformation between local and global coordinate system. Is nothing but it is simply a relation consisting of direction cosines. You can see there small x small y is related to capital X capital Y through the angle between local x axis to the global x axis, that is cosine of angle small x capital X, that is angle between local x axis and global x axis. Similarly, the first component is cosine of small x capital X, second component similarly it is cosine of small x capital Y, that is angle between global local x coordinate system to the global y coordinate system. Similarly, the component at 2 1 location, that is second row first column location, is cosine of small y capital X, and at 2 2 location, that is second row second column, it is cosine of small y capital Y. And if alpha is the angle from global x axis to the local x axis measured in counterclockwise direction, this direction cosine matrix becomes cos alpha sin alpha minus sin alpha cos alpha. So, the relation between the global coordinate system and the local coordinate system is given by this equation. And for an arbitrarily oriented element, if x1 capital X1 capital Y1 capital X2 capital Y2 are coordinates of element ends, then the components of this transformation matrix can be obtained using the coordinates of the element ends, which is given here in this equation. Sin alpha is y2 minus y1 over L, cos alpha is x2 minus x1 over L, where L is length of that particular element, which you can easily obtain using the once we know the coordinates of element ends in this manner. So, using this we can easily get the transformation from global x axis y axis to the local x axis y axis, or in the vice versa. And now now we are interested in the relationship between the local displacement vector and the global displacement vector. And please note that local displacements gets transformed in the same manner as coordinates, spatial coordinates. So we know that the transformation between local x axis, y axis and global x axis, y axis. So this d1, which is a local displacement at node 1 in the x direction, is related to the global displacements u1 u2 in the capital X capital Y direction in the same manner as small x is related to capital X capital Y, that is d1 is equal to cos alpha u1 plus sin alpha v1. Similarly d2 is cos alpha u2 plus sin alpha v2, which can be written in a matrix and a vector form in the manner shown in the slide. And this can be compactly written as dl is equal to t times d. dl is nothing but displacement vector in the local coordinate system, and d is displacement vector in the global coordinate system, and t is transformation matrix, which is cos alpha sin alpha 0 0 0 0 cos alpha sin alpha. Please note that this transformation matrix is a is an orthogonal matrix, that is T transpose is same as, it can be easily verified that T transpose is same as T inverse, or T transpose is equal to identity matrix. So the inverse relation, that is D is related to DL via D is equal to T transpose DL, since T is an orthogonal matrix. So this local equation system, that is RL equal to KL DL, now we can replace DL with T times D, and now multiplying on both sides of this equation with T transpose, we get T transpose RL is equal to T transpose KL T D. And note that T transpose RL is nothing but R, because T is an orthogonal matrix. So it can be easily verified that transformation matrix is such that the quantities from local to global coordinate system can be transformed as T transpose DL is equal to D R and T transpose RL is equal to R. So in the previous equation where we have T transpose RL, we can replace that with R, and we can define K as T transpose KL times T. So we get KD equal to R. So what is K here? K is T transpose KL T. KL is nothing but it is stiffness of an axial element, and T is nothing but transformation matrix consisting of direction cosine components. So where K is the stiffness matrix for 2-dimensional truss element. So carrying out the multiplication, carrying out the required matrix operations, we get for the plane truss element the equation system in this manner. So once we know the ends, the coordinates, spatial coordinates of ends of a plane truss element, we can easily assemble, and once we know the material properties and geometric properties, we can easily assemble the element equations for a truss element using this equation system. And the nodal displacements for any 2-dimensional truss can be computed using this equation. Once nodal displacements are known, the axial forces, stresses, strains in the elements can be computed by first calculating the local element deformations. That is, here when we solve this equation, we get u1 v1 u2 v2. Please note that u1 v1 u2 v2 are the displacement components in the global coordinate system, global x, global y coordinate system. We need to convert them back into the local coordinate system before we calculate strains. So that is why we need to first compute the local element deformations, and then using shape function for axial deformation element we can calculate strains, and then from strains we can calculate stresses, and then from stresses we can calculate the axial forces, elemental axial forces. So this is the relation between local displacement vector and global displacement vector. So using the values of u1, v1, u2, v2 we can back calculate what is d1, d2 using this relation. Once we get d1, d2 we can calculate element strain, and once we get element strain we can calculate element stress, and we can calculate element axial force. So now we can solve an example, to understand the concepts that we learned now. Find axial forces and nodal displacements for a plane truss shown below, and assume cross section, area of cross section of element 1 to be 1000 millimeter square, and that for element 2 to be 1500 millimeter square, and material property Young's modulus is 210 GPa, and the truss is shown there and all the dimensions are indicated. And the first thing we need to do is the choice of local node numbers, and the choice of local node numbers defining elements called element connectivity is arbitrary. However, this choice determines the direction of local x axis, small x axis, and it is important to remember for proper interpretation of element quantities. So definition of local x axis is important. For example, for element 2 if we choose first node, for element 2 if we choose first node to be node 1 and second node to be node 3, then positive direction of local x axis for this element is same as global y axis. Hence angle alpha, which is nothing but angle between the local x axis and the global x axis, it turns out to be 90 degrees. However, if we choose to define element 2 to go from node 3 to node 1, then positive local axis for element is along negative global y axis, giving alpha value equal to 270 degrees. A consistent pattern for defining element connectivity is helpful when analyzing stresses with large number of elements. So it is very important, the choice of local node numbers is very important. So now for this particular problem the node numbers are shown there in the figure, and also global degrees of freedom are indicated in the figure. That is, at node 1 we have 2 degrees of freedom, u1, v1. In the global x axis direction displacement is u1, global y axis direction displacement is v1. Similarly at node 2 u2, v2, and at node 3 u3, v3. So looking at the element connectivity, element 1, the first node is local node 1 is global node 1, local node 2 is global node 2. For element 2, local node 1 is global node 1, local node 2 is global node 3. So for element 1 it is the node numbering is given such a way that element goes from node 1 to node 2, and length of this element is 500 millimeters, and the distance between 2 and 3, node 2 and node 3 is given as 300 millimeters, and the distance between node 1 and node 3 is given as 400 millimeters. So it turns out the distance between node 1 and node 2 is 500 millimeters. So length of this element is 500 millimeters. Since the element, the coordinates of element 1, the coordinates of ends of element 1 can easily be calculated. or looking at the geometry, we can easily find the angle between global x axis and local x axis for element 1 is given by cos of that angle is equal to 0.6, and cos of the angle between local x axis and global x axis for element 1 is 0.6, and sine of angle between global x axis and local x axis for element 1 is 0.8, and using these values we can assemble the element equations for element 1. And here if you see the element equations, loads applied at node, actually load is applied at node 1, and the loads applied at node 1 can arbitrarily assign to any of the elements, that is you can assign those loads to element 1 or element 2, but here it is assigned to element 1. Alternatively the nodal loads can be assigned to global load vector directly. In this example, the applied load at node 2 is arbitrarily assigned to element 1, sorry, it is at element node 1, the load is applied at node 1, so it is arbitrarily assigned to element 1, that is minus 100 cos of pi over 4, 100 sin pi over 4, and this is the equation system for element 1. Similarly, we can assemble the equation system for element 2, noting down the angles which the local coordinate system makes with global x coordinate system. And if you look at element 1 equation system, we should now make a note where the contribution from element 1 goes into the global matrix. Please note that local in the local coordinate system, the degrees of freedom or the displacement vector u1 v1 u2 v2 corresponding to element 1 is same as global u1, global v1, global u2, global v2, and the row number in the global matrix, the row number and column number in the global matrix are nothing but 1, 2, 3, 4. So the locations into which the contribution from element 1 equations goes into the global equation system is given by the global matrix, locations in global matrix given in this slide. So 1 1 location, whatever is there at 1 1 location in the element equation for element 1, it goes into the location 1 1. Similarly, whatever is there at location 4 4, it goes into the 4 4 location of the global equation system. So now let us look the equation system for element 2. Element 2, local node 1 is 1, local node 2 is 3, and the angle between local x axis and global x axis, based on that cos of that angle is 0, cos of the angle between local x axis and global x axis is turns out to be cos 90, which is equal to 0, sin 90 is equal to 1, and substituting the direction cosine values into the element equations along with the length of the element, Young's modulus of the element, length of this element is 400 millimeters. Substituting all these values, the element equation system for element 2 turns out to be this. As you can see here, since we already assigned load which is applied at node 1 to element 1, we are here again it is not assigned to this element. So now let us see where the contribution from element 2 goes into the global equation system. This is the elemental equation system for element 2, and based on the local displacement vector u1 v1 u2 v2 corresponding to element 2 corresponds to the global corresponds to the global locations or the row number in the global matrix 1 2 5 6. So, the location the global matrix is based on the row number given there, row number in the global matrix. So, the corresponding locations in the local, corresponding values in the local equation system, the contribution of those goes into the global locations shown in the slide there. That is whatever value at 1 location, the local elemental equation for element 2, the contribution goes into the global 1 location. Similarly, whatever value is there at the location 4 in the local stiffness matrix, it goes into the 6 location in the element global equation system. So, based on this we can assemble the global equation system, and here it is indicated, you can see here for the given problem node 2 and 3 are fixed. So, the corresponding degrees of freedom values will be equal to 0, and the only unknowns are u1 v1, which corresponds to the degrees of freedom for node 1, and wherever 0 value is applied, 0 value for the degrees of freedom is applied, reactions will be developed at those points. So, since displacement degrees of freedom values at node 2 node 3 are 0, corresponding in the corresponding locations in the force vector, reactions terms will be there. So, they are indicated using r x2 r y2 r x3 r y3, and to solve this equation system what we can do is we can actually ignore rows and column corresponding to 0 specified displacement. If the specified displacements are non-zero, then we need the columns corresponding to these specified degrees of freedom which are non-zero, but in this case what happens is we can actually ignore the rows or delete the rows and columns corresponding to the degrees of freedom for which the value is 0. So, we can eliminate the rows and columns 2 to 4 2 to 6, 2 3 4 rows and 3 4 5 6 rows and columns can be deleted. Deleting the rows 3 to 6, we get reduced equation system, and solving this equation system we can find what are the values of u1 v1. So, we obtained this equation system by deleting the rows and columns at the location 3 4 5 6, which corresponds to the global degrees of freedom of node 2 and 3. Since the global degrees of freedom of node 2 and 3 are 0, we can delete those the corresponding rows and columns, and we obtain this equation system, and solving this equation system we get u1 v1. So, once we get u1 v1, we can go back to each element and we can calculate stresses, strains, stresses, axial forces in that element, but before we do that we need to find what are the corresponding local values. So, for element 1, local displacements using the global displacements, that is u1 v1 we just calculated, and u2 v2 are 0. So, using these values, and also for element 1 we know what is cos alpha sin alpha. So, we can find what are the local displacements, and using the local displacements we can calculate the element strains and element stress and axial force, and axial force turns out to be positive. So, it is tensile force. Similarly, for element 2, local displacements can be obtained using global displacements u1 v1 u1 v1 just we calculated, and the values that we calculated using they are nothing but u1 v1, u2 v2 global displacements, u2 v2 for element 2 corresponds to u3 v3 which are 0. So the local displacements can be obtained in this manner. Once we get local displacements, we can calculate strains, element strains using this relation. Element stress, and it turns out that element strain is negative quantity, that is compressive, and element stress also turns out to be negative, and element axial force turns out to be negative. So it is compressive force. So the member is in compression. So now we have seen, just now we have seen 2D truss problems, how to solve 2D truss problems. This in a similar manner a truss having any number of elements can be analyzed. And now let us look an example or first derive the equation system for a 3D truss problem, 3D space truss, whereas 2D truss is a plane truss, 3D truss is going to be a space truss, and 3-dimensional space truss element can be developed using a coordinate transformation and using local elemental equation for axial deformation element in the manner which we did for 2D plane truss element. Here a 3D space truss is shown, and the local degrees of freedom are indicated are identified as u1 v1 u2 v2, and the global x axis, y axis, z axis are shown there, and the local displacement at node 1, node 2, d1, d2 are also shown. Similarly the global degrees of freedom at node 2 u2 v2 w2 are shown there, and the local x axis is oriented along the centroidal axis of the element, space element. So the local displacement vector is local displacement vector consists of 2 components d1 d2, and the global displacement vector consists of 6 components u1 v1 w1 u2 v2 w2. Similarly global local force vector consists of 2 components capital P1 capital P2, and global force vector consists of 6 components F1 x, F1 y, F1 z, F2 x, F2 y, F2 z. So the notation that we are following is similar to what we used for 2D plane truss, and what we require, the important thing is transformation matrix. The components of the vector in the local x, y, z coordinate system are simply projections of its capital X, capital Y, capital Z components, that is the global components. So the relation between the local spatial coordinate system to the global spatial coordinate system is given by this equation, which is just an extension of what we have seen for 2D plane truss problems. You have one more dimension, additional dimension, so the corresponding components appears in the transformation matrix, and the coordinate system vectors. The cosine of small x capital X is denoted using Lx. Similarly other components are denoted using Lx, Mx, Nx, Ly, My, Ny, Lz, Mz, Nz. These are nothing but direction cosines. And similar to 2D plane truss element, the displacement components or displacement in the x direction transforms in the same manner as spatial coordinate in the x direction. So d1 is given by Lx times u1 plus mx times v1 plus nx times w1. Similarly d2 is given by Lx times u2 plus mx times v2 plus nx times w2. These two equations can be written in a matrix and vector form in this manner. D1 D2 is equal to Lx Mx Nx 0 0 0 0 0 0 Lx Mx Nx U1 V1 W1 U2 V2 W2, and this can be compactly written as dl is equal to T times D, where dl is local displacement vector, T is transformation matrix, and D is global displacement vector. And transformation matrix, as you can see here, it is different from what you have seen for 2D plane truss element, and this transformation matrix can also be verified to be orthogonal matrix, that is T transpose T turns out to be identity matrix, or T transpose is same as T inverse. So the inverse relation, that is D is equal to T transpose DL. Given the element nodal coordinates, the direction cosines can be computed. Once a spatial element is given, once we know the spatial coordinates of ends of that element, we can calculate Lx Mx Nx using these relations, where capital L is nothing but length of that element. Length of the element can be obtained using the coordinates of the ends of the element using the relation given here, and the relation between the element stiffness matrix and the global coordinate system to the local coordinate system, the equation looks similar to what we derived for 2D plane truss element, except that transformation matrix T is different. Here now it is Lx Mx Nx 0 0 0 0 0 0 Lx Mx Nx, and KL is same as what we used for 2D plane truss element, because the local stiffness matrix is same, that is E A over L 1 minus 1 minus 1 1. So using these transformation matrix and local element stiffness matrix, we can get the global equation, element equations for a 3D truss element in this manner, and it is easy to memorize this equation system without much effort. If we just one quadrant of this, if we remember one quadrant of this, the components in one quadrant of this stiffness matrix, we can write the components in the other quadrants, that is whatever elements you have in the first quadrant, the components in the fourth quadrant of this stiffness matrix are same. First quadrant and first quadrant are same, and whatever components are there in the second quadrant and third quadrant, they are nothing but with a negative sign appended to whatever components are there in the first quadrant. So in that manner we can easily memorize this stiffness matrix for 3D truss element, and E A over L is just they are material and geometric parameters, and the displacement vector consists of U1 V1 W1 U2 V2 W2, and similarly force vector consists of 6 components. So once element equations are written in terms of global coordinates, the assembly and solution process proceeds in a same manner as we have seen for 2D truss element. Axial forces can be computed by transforming displacements back to the local element coordinate system. So once we get the global displacements, we can calculate local displacements. Once we get local displacements, we can calculate strains and then stresses, and using those values we can calculate the forces in a truss element, 3D truss element. The equation is given here, and this equation in terms of direction cosines after manipulating the first equation is shown there. So to understand these concepts, let us solve a 3D truss problem. Find joint displacement and axial forces in a cantilever space truss shown all supports are in xy plane. The coordinate system global x, global y, global z coordinate system is also indicated in the figure. The cross sectional areas of member 1, 4, 2, 4 are 200 millimeter square, and that for member 3, 4 is 600 millimeter square. Young's modulus is 210 GPa or kilonewton per mm square, and because Newton per mm square is MPa, kilonewton per mm square is GPa, all units are in SI units. So, looking at this the various dimensions that are given here for this 3D space stress, we can easily identify what are the x, y, z coordinates for each of the nodes 1, 2, 3, 4. And now again here for simplicity, the element equations are directly written in terms of global degrees of freedom while taking into consideration the boundary conditions. The unknown reactions at ith node corresponding to 0 displacements are identified as r xi, r yi, r zi. I takes values 1, 2, 3. It is similar to what we did for 2D plane truss elements. So, now for element 1 goes from node 1 to node 4, that is local node for this local node 1, node 1 for this element is global node 1, global node local node 2 for this element is global node 4. So, using the nodal values, all are given, all the units are here in millimeters. So, the coordinates are given there for node 1, node 2 for element 1, and using these values we can easily calculate what are the direction cosines using the values difference between the spatial coordinates dx, dy, dz, and since we know the coordinates of end points, we can easily calculate what is the length of this element, and we can calculate what are the direction cosines Lx, Mx, Nx, and material properties, cross sectional areas and the length we just calculated. So, using those values we can easily write the element equations for this particular element using the formula that we just developed for 3D space truss element. Similar process can be repeated for element 2 and element 3. Element 2 local node 1 is nothing but global node 2, local node 2 is global node 4. So, using this information, again all units are in millimeters, we can calculate using the difference between the spatial coordinates, we can calculate dx, dy, dz, and length of the element can also be calculated, and direction cosines. And material, using material properties and geometrical properties, we can calculate elemental equations for element 2. As already mentioned, since node 1, 2 and 3 are fixed, the corresponding degrees of freedom are 0, and the corresponding locations in the force vector reactions will be at the corresponding location, reactions will be developed. So, those are indicated using Rx2, Ry2, Rz2. Similarly, in the earlier equation we have Rx1, Ry1, Rz1. Similarly, we can assemble the element for element 3, the equation system, it goes from node 3 to 4. So, local node 1 is 3, global node 3, local node 2 is global node 4, and we can calculate dx, dy, dz and length, and we can calculate direction cosines, and we have the material properties, again geometrical properties. Using this we can calculate what are the element equations for this particular element, and now we have the elemental equations for element 1, 2, 3, and now we are ready to assemble the global equation system. But since at each node we have 3 degrees of freedom and there are 4 nodes, so global equation system will be 3 times 4, that is 12 by 12, and it is very cumbersome to write a big 12 by 12 equation system. Instead of that, with the reasoning that since node 1, 2, 3 are fixed and the corresponding degrees of freedom are 0, and we have seen from the 2D truss problem in the global equation system, finally when we are solving for the unknown degrees of freedom, what we will be doing is we will be eliminating the rows and columns corresponding to the degrees of freedom at which 0 value is applied or 0 value is specified. So finally in the global equation system, to solve for the unknown degrees of freedom, we need to eliminate those rows and columns corresponding to the degrees of freedom of which the value is 0. So anyway in the global equation system we will be eliminating the rows and columns corresponding to nodes 1, 2, 3, which are nothing but for the node numbering that we have given, these corresponds to the location 1 to 9, that is 1 to 9 rows and columns will be eliminated in the 12 by 12 equation system. So whatever we will be left with in the reduced equation system will be at the locations 13, 14, 15. So we can directly write the global equations corresponding to these degrees of freedom. So this is what I just mentioned, nodes 1, 2, 3 are fixed, so the corresponding degrees of freedom are 0. So we can directly write the reduced equation system which corresponds to the global equation system locations 10, 11, 12 locations. So this is the reduced equation system which is obtained by summing up the contribution from element 1, 2, 3 at the locations in the lower quadrant of these element equations. The contribution is taken from there, and once we add up we get this reduced equation system. We can solve this equation system for the unknown degrees of freedom which are U4, V4, W4. This is a 3 by 3 equation system, so those unknown U4, V4, W4 can be easily solved. And once we solve for U4, V4, W4, now we are ready to calculate the elemental forces by calculating strains, stresses. So computation of axial forces can be calculated using this equation. For element 1, applying this equation and noting that for element 1 local node 1 is same as global node 1 and local node 2 is same as global node 4, and with that understanding the axial force in element 1 is given by this, and it turns out that this element is in tension. Similarly element 2 also it turns out to be in tension. Element 3, it turns out that this element is in compression. So in this lecture we have seen how to solve 2D truss problems and 3D truss problems. and one of the important thing is assembling of a global equation system, or we can also obtain directly the reduced equation system by calculating or doing all the calculations in brain, that is directly writing the reduced equation system by eliminating the rows and columns corresponding to the degrees of freedom in the global equation system at which the degrees of freedom are specified to be 0. So that is what we adopted in the second example, which is a 3D truss problem. So in the next lecture we will be seeing how to solve the truss problems for temperature changes, stresses due to temperature changes and lack of fit.